What's up, everybody? This is Matt Brown with another IoT hacking video. Today we are doing a follow-up on the proprietary encryption protocol that we discussed in the last video in this Chinese security camera that we have been looking at. And I'm really excited because you, the viewers and the followers of this channel, have really chimed in the comments and on the GitHub repository. And so we're going to go ahead and look at some of the ways that you helped me understand the reverse engineering of this encryption protocol, and then how all those comments made me think again about this encryption protocol, and now we have an even better break of the protocol that does not even assume that we have corresponding decrypted data to compare to the encrypted data. So at the end of this, purely through mathematical statistical analysis of encrypted data that we have obtained off of the wire, we're going to be able to derive the encryption key and then obviously use that key to decrypt all the messages we want to. So let's first go ahead and look at the GitHub page, because I had so many people reach out to me through different mediums, but what was really cool to see is a number of pull requests that appeared in this repository. But this is the pull request I specifically want to talk about. And first I want to talk about a comment that's located in it. And that is the key. And there was some question in my mind initially what the key was. And we have now determined, a number of people in YouTube comments and here in this comment on the pull request are stating that the key that is fed into this function, so let's go look at this function again in Ghidra. So right here, this parameter, this is what gets used to generate what I was calling this variable, this local integer variable. I was calling that a seed. It's probably better to call that actually the key. So what it's doing is it's having a string, a piece of text that's fed into here, and then in this for loop, it is generating a 4-byte key out of that string. And then from that point, the key is the thing that gets used to send into this table, which then derives the correct byte to pull out of the table to perform an XOR and actually do the decryption or encryption, depending on the operation. So let's actually go ahead and look at this commit. And I also, in the local repository, I already have this pulled down, but thank you so much to Mexo2, I hope I'm pronouncing that right, who just provided this really well written piece of code. And I had to fix a couple things in it, or I had to fix one thing in it and then add to it. And so what we're going to do is we're going to actually go over here where I have already pulled this change down, and we're going to look at some of this code together. So here we recognize this lookup table. We talked about this in the last video. We got this right in here. So we can see that this is just a globally defined byte array of 256 values that clearly gets pulled out of this function here, and then it gets passed back to perform the XOR operation for the encryption and the decryption. And so that's that's nothing new. Here is what we are going to have to make a change here, because this was almost correct, but it was wrong for some data. And so what I need to add to this are these operations, which we can go back over to Ghidra. So we do need to either, you could do mod 256 or in the byte ff. Either way, same thing. So we're just going to actually add this in to our C code here. So let's take our data, and then we also want to do the entire thing because it could also overflow those bounds when we add in this C key here. And notice before I was calling this a seed. Calling it a key is actually the better understanding. And this was actually the real breakthrough that I was not understanding, and all of you people who commented on YouTube really helped me understand this. So I want to go back and really explain where I was not thinking clearly. It's really hard to understand how I was not understanding it now that I've seen how it works. So this value is better understood as a byte array of length 4. And so once you realize that, you see what's happening in these functions. Once you kind of deobfuscate all this stuff, it's just using this string to kind of mix around the string a little bit, and then to set those 4 bytes to some random values. It's determined based on the key string here that we're sending in as a character array. And so, but once you have that value, what it does is it gets passed into this function here, and then it gets passed in as a pointer. That's what I knew it was getting passed in as a pointer, but I didn't realize the full implications of that, because what's happening right here when so this is where that, key, array gets passed in. What's happening to it is we're adding the second parameter and then mod 4, or logical and 3. And so what that's going to do is it's going to pick, it's going to pick a value. It's going to pick one of those bytes. And this is actually the whole key. Like, this concept right here is what led me, like, the light bulb turned on, and I was like, whoa, we can perform a absolutely worse attack on this protocol. We can break it without any of the corresponding decrypted data that I got in the UART shell in the last video. We don't need that anymore at all. We can just grab data off the network, data that's large enough so we can perform the statistical analysis in a good way. We'll get into that later. But what the key takeaway we want to have here is that because this is dereferencing this key array, the key array, it's only one of those bytes is in effect for any one byte decryption. So they are independent. Each byte is independent from all the other bytes. So what this means is, let's just do some math to talk about what that means. So if you have a 4-byte value, so that you could represent that as 2 to the 32, right? So you have 8 bits in each byte times 4, 32. A bit can be 2 values. It could be 0 or 1. That's how this math. And so we get that number. So you would have to guess that many keys. There's that many possible keys that could be the true key. Another way to think about it is that a byte has 256 values, and when you combine 4 of them, you get this number. Again, you see that those are the same. But if each byte was independent, then this is not the correct representation. This is the representation if there is a dependence, if the bytes taken together are used to perform the decryption. But they're not. So 1/4 of the data uses the first byte, 1/4 of the data that gets decrypted uses the second, and so on. And so the correct math to perform is just 256 times 4. So there are only 1,024 guesses that we're going to need to make, because we can attack each byte of the key independently. So because they're not dependent on each other. That is huge, and that's what's going to allow us to completely attack this in the end. But I am getting slightly ahead of myself. So I'm just getting excited about this. So here we fix up this function, and now we need to add a main menu. So we're going to int main. We'll have it return, because that's a good idea. Okay, so to use this function, what we're going to do is we're going to go grab it up here, And so it takes in a string, and then, you know, we'll just call this in, out, so, and then size. And then at the end of all of that, what we're going to do is we're going to say printf, and then we're going to say, this should be a nice ASCII string. Oh wait, actually, okay, so we have to kind of do this a little bit different. It's actually kind of annoying, but what we're going to do is we're going to say for int I equals 0, I is less than size, because the first 16 bytes are not text data, and it will like interrupt, and if there's like a null byte or something like that, it won't print out like all the data. So that's why I'm doing this. And then wait, I plus plus, let's do that. And yeah, unfortunately, we're gonna have to print these all independently. So we're just gonna do like print one char at a time. Out of I. There we go. I think that's all correct. We're gonna find out. I'm not the world's. I've never claimed to be the best C programmer in the world, so we're just gonna see how this goes. All right. So the key, as we were told over here. Let's go back to the conversation. The key value. Wait, where is it? Is VStarcam 2019. So fun fact, that is also like the root password on a ton of these devices. So that's kind of fun. All right, here we go. All right, now we obviously need to define what our input and our output are. And so we're going to grab okay, so we're going to have like a char in equals this thing, and I actually have a helper function. I'm gonna I'm just gonna copy and paste this from my other screen. Okay, so there we go. This is the message that was like the first one that I ever decrypted in the last video. So we should kind of recognize this. Okay, so what we're gonna do then is we're gonna say int size equals string length of in, and we're going to say char out equals malloc of in. There we go. All right. That might work. It might not. And then it's also going to tell me what all the problems with this is. Okay, so say original. Aha, yes, I need to import this. Aha. So you can see there that it did successfully decrypt this message, which is awesome. And so we're actually going to use this code to get a little bit more information about this key process here. So here we can see that this code has refactored that obfuscated, decompiled code that was just this kind of opaque variable into a 4-byte array. And so what I actually want to do is I actually want to print out what the values of the actual underlying key is, right? So it's taking in that string, VStarcam 2019, and then it's turning that into this 4-byte key. And I want to figure out what the 4-byte key is, because that will let me validate my statistical attack that I'm going to perform. It'll allow us to see if it's working or not. And so what we're going to do is we're going to print out a decimal. So we'll just call this like key 1. And then, oops, actually call it 0. There we go. That looks good. Now just do it all 4 bytes. So remember, these are all independent bytes being, it gets used independently in the next step, I guess I should say. So let's compile and run. And here we can see that the key is, 45. So these are the different key values, the different byte values that are getting determined to be the key and then get used later on. So let's just, I'll actually just kind of save these up in the corner right there. Nice. I never use that space. All right. So now what we're going to do is we're going to look at a program that I developed here that is going to perform a statistical analysis of the encrypted data with absolute no knowledge of the decrypted value, any of that attack we were doing before, and we're going to see how this works. So most of this is the same. Here you can see the function that was changed, that was updated to kind of fix the slight error in the what was committed into my repository in that pull request. And let's keep going down here. Okay, so here you can see that I've completely commented out the generation of this key. I am not going to generate the key based on that string that gets inputted. We're not doing that anymore. What we're going to do instead is I'm going to kind of walk you through this code. I'm not going to type all this on the fly because this did take me a little bit of time to perform. So we're going to loop through all of the possible key bytes one at a time. So the byte 0, 1, 2, and 3. And so for each of those, we are going to determine which value of that key we like the best, we think is the most likely to be the key at that certain byte location. And the reason why we can do this attack, again, is because each of those bytes is independent of all the other ones. When it decrypts a certain part of the message, it's only going to be using one of those bytes at a time. And that's what's really going to enable this attack to work. So then we're going to loop through, 0 to 255 every byte value. And what we're going to do is we're just going to set the key to that value. And we're going to run through every possible combination of what that one key byte could be. And then what we're going to do is we're going to perform the decryption, and then we're going to do something right here that is the key to all of this. We are going to count in the full decrypted value how many printable ASCII characters there are in the decrypted result. Because if we assume, and much of this protocol, what's actually being sent inside of it is text-based data. So a byte has the full range from 0 to 255, but ASCII data is limited to being greater than or equal to 32 and less than or equal to 126 in decimal. And so what we're going to do is we're going to keep this count for each potential key byte. We're going to keep a count of when we use that to decrypt the message, how many ASCII characters are there. And so we do that, and then I'm going to determine, I'm going to keep track of which one is the best, and I'm going to determine that based on which one has the most. I'm going to keep track, and so if the best key count, or if the new if the new one that gets decrypted, if the number of printable characters is more than what I've seen so far for a certain byte location, then I'm going to update what I think is the best key for that spot. And then I'm going to do something cool here. This is not necessary, but this is just so we can visualize how this statistical attack is kind of working. So I'm going to take the number of printable characters that happens in the decrypted result for a given key value, and then I'm effectively dividing by 10 here. And then we're going to print out a star. So for each key value, it's going to print a bunch of stars across the screen. And then we're going to be able to scroll up, and there should be one outlier that has more ASCII text than all the other potential key values at a given byte location. So we're going to do that, and then, whoa, yeah, they have a bunch of data there. And then at the end, I'm going to print out K0, 1, 2, 3, 4. And so, again, we absolutely commented out the code that calculates it based on the known string. We're at the end of the day, the best key is going to get set to that spot based on our statistical analysis, and we should see the same exact key come out. So these values, when we run this program, should match what we have over here. And then you're going to see a massive packet here. So because this is a statistical analysis on the data, the bigger a packet I have, the better. So this is a packet that is the max size in our UDP protocol. It's 1,032 bytes, I believe. And so, oh yeah, there we go. So I just hard-coded the length in. This is sent to here, but we can just, change this. So doesn't matter. Okay, so that string doesn't get used at all anymore. So we don't even care about that. All right, so what we're going to do is we'll just use this string. We're going to call that. Okay, and now we're going to run our program, and this is the moment of truth. And we have all of those same key values printed out at the end. So we were able to completely, with that, a decrypted packet. So all we'd have to know is we have to know the protocol. We have no knowledge of that key phrase that generates the key, and we can determine the key using select large packets. Or you could combine a bunch of packets together and use it as a larger data set. Either way. But now I'm going to show you with these stars that we have printed out here for each potential key value. I'll do it for a couple of the bytes here, and so we're just going to scroll up, and so we're going to see, okay, we kind of have everything is located at the same spot. Oh, look at that. There's that statistical outlier there for our last, so that's the last key value. I'll scroll up for one more. So here we go. We've got, all these stars. And, oh, there's our other outlier. So you can see that there is actually a statistically significantly greater amount of printable characters that's generated when you select the right key. And again, this is all possible because each of those bytes is independent. If they were dependent, you would have to guess each of them. You'd have to guess all of the bytes. You'd have to guess the entire 32-bit key correct to get a statistically significant amount more of ASCII data out of it. It's at that point it is all or nothing, and that is how a good encryption algorithm works. Is one small change in the key or one small change in the data massively should change the output. But that's obviously not happening here. I want to thank everyone for commenting on the YouTube video. There's a really cool community that we're building together. If you're not on the Discord, I would encourage you to get on Discord. If that's not a privacy concern, I understand that for some of you, you don't want to do that stuff, but thank you for giving me pull requests. There's like 2 more pull requests that I've seen now in the GitHub repository. So thank you for following this work. Please let me know down in the comments what you thought of this video and what I should do in the future. Thank you and have a good day.